Hello and welcome. So we're going to be talking about radians, arc lengths, and area of a sector today. So when we're talking about radians, a couple of things to mention. So radians versus degrees, they're essentially both doing the same thing. It's kind of like the difference between feet versus meters. They're both ways to measure distances. They just do it differently, but they're still doing the same thing. Right? I don't know how helpful that is. But radians, degrees both measure how far around a circle you've gone. The degrees measure it, with the central angles, right? Going all the way around a circle is 360 degrees. Versus radians is that they use the measure of the angle by looking at how much circumference of the circle that you've covered. So, for example, when we're looking at a circumference of a circle with radius 1, remember, formula for that is circumference equals 2 pi times the radius. So if we're looking at a radius of 1, it's literally just plug 1 in, the circumference is 2 pi. That means that if I was looking at only halfway around my circle, right, if the whole thing is 2 pi, then halfway is just pi, and it measures by circumference as you go around. All right, so that means that for a unit circle, meaning a circle with radius 1, that means that 360 degrees is equivalent to 2 pi, right, in radians, right, 2 pi radians. So do keep that in mind, that is an equivalent. So if I wanted to make this a little easier for conversions, I'm going to say 180 equals pi, right? Half of the circle in degrees is half the circle in radians. Now, don't worry about this. Yes, we use radius 1, but the radian measure would end up changing if you go off of the unit circle, meaning radius larger than 1 because the circumference is larger. And there are ways to make up for that. That's where we're talking about arc length and area of a sector next. So hold off on that question. But for now, keep in mind 180 degrees equals pi. So if we're doing any conversions, keep in mind, right? If I have the same thing over the same thing, we get 1. It simplifies, right? Those cancel, leave you with 1, you're good to go. Now, when you're looking at conversions, if I have something that is a degree, the only way it's going to cancel is if I have something that's also a degree in the bottom, which means those are gone and it would leave you in the radian measurement. So in order for that to happen, we'd say, okay, use your conversion. You don't have an equation, so you can only multiply by 1. So I'm going to put 180 degrees on the bottom and pi on the top. Now you might be thinking, hold on. I know that pi is 3.14159 so on and so forth, right? Over 180, clearly those numbers does not give you 1. It does, keeping in mind that that's 180 degrees and this is pi radians. It's like saying 1 foot is the same as 12 inches. They are the exact same thing. That's the exact same distance. You're just saying it 2 different ways. That's what we're doing with the pi and 180. So if you need to go from a degree into a radian, times by pi over 180. Vice versa, if you start with a radian and you want to go into a degree, then you just essentially flip that, take the reciprocal, or you times by 180 degrees over pi. And that'll put it into degree for you because your radian essentially will end up canceling with your radian and you get a degree symbol left. So then the question is, how do I know something's in radians versus degrees? Degree is actually really easy. This is in degrees because you see the degree symbol, right? And we know that this is a radian because it doesn't have the degree symbol. So, like, if you have 5, is that a degree or a radian? It is a radian. The pi does not have to be there for it to be a radian. 5 on its own is considered a radian value, unless you have the degree symbol, in which case it's now a degree. So you know if something's in degrees or radians if it has the degree symbol or it doesn't have the symbol, right? If there is no degree symbol, then fun fact, you're looking at a radian, whether it has a pi on it or not. So do keep that in mind. So if we're looking at a degree, then times by pi over 180 degrees. Because then your degrees cancel and you're left with, right, that's technically over 145 pi over 180, because fractions multiply straight across. Simplify your fractions, right? 45 and 180, the common number is 45, right? It goes into itself once, into 180 4 times. So pi divided by 4, right? 1 pi, which is just pi, right, is your answer. So 45 degrees is equivalent to pi over 4. And we can do that for all of these, right? If it's a degree, times by pi over 180 degrees. Degrees cancel, we're left with 215 pi over 180. Simplify the fractions. Common number is a 5 on this one. So this will cancel, gives you 43. This cancels, give you 36. And you're left with 43 pi over 36. Answer, you're done. If it's negative, nothing changes. You literally still do times pi over 180, right? Degree symbols cancel. Common number is a 20 on this one. 20 goes into its 200 10 times and into 180 9 times. The negative is just negative, so it's just negative 10 pi ninths, done, right? Degrees into radians, not hard. Other direction, radians into degrees. Well, now there's no degree symbol, which means we want pi in the denominator. And because there is a pi, it actually cancels very nicely for us. And we get 180 degrees over 6. Simplify that. 30 degrees. Answer, you're done. Same thing. There's no degree symbol, which means this is a radian value. Times pi on the bottom. Those cancel. 360 degrees over 5. Or in other words, that is 72 degrees. Finished. Right? There's not a lot here. It's really just a matter of making sure you recognize what you're staring at, right? And you're good to go. Okay. Now this one, read your directions as to what your answer is requiring. This is not going to simplify nicely. This is going to be negative 45 halves when it simplifies. It's still a degree value, right? You could leave it as a fraction. Typically in degrees, though, we usually use decimals, so you can say negative 22.5 degrees. Either or statement for that one. But that's conversions in a nutshell. Okay? So let's move on to arc length. Arc length, there's a couple of ways we can talk about this. Remember, an arc is a section of the circumference. So if I wanted to look at this arc specifically, and I wanted to find the length of that arc, you're looking at a portion of the circumference. You say, okay, well, remember, circumference of a circle was 2 times pi times the radius. All right, so in our case here, our radius is 2 feet, so c equals 2 pi times 2, or in other words, 4 pi. That means the entire outer edge of the circle is 4 pi. Well, then how do I find just that arc? Well, think about it this way. How much of the circle do you have there? Now, typically, I'll have a lot of students who say, oh, we only have a quarter of the circle. In which my question to you is, how do you know? And the answer is that 90 degrees. Remember, snow cone it, find the intercepted arc, right? That pink arc, what we're trying to find is 90 degrees of the entire 360 degrees, or in other words, 1/4 of the circle. So how we're going to run this is we're going to say, okay, I know 4 pi is the entire way around, and we're taking 1/4 of the 4 pi, or in other words, pi is the length of just that arc, right? Which means that your arc length formula, and all the ways you're going to find it, is you're essentially going to find the circumference, 2 pi r, and you're going to multiply it by the percentage of circle that you have. So your angle, I'm going to use theta as the variable for the angle, right? So your angle over 360. And that's it. That's as hard as this needs to get. So find the circumference and then times it by how much of the circle you're looking at. Would your formula change for radians? Yeah, you would just say how much you have in the circle in radians, right? The circumference. And then, oh my gosh, I just lost my train of thought. And then you can give the radian angle over 2 pi. Oh, that was a struggle. So you can do the equivalent in radians. There's a lot more simplifying that radians would have. There is a specific formula for arc length in radians. If you want to Google that, you're totally welcome to. But I'm going to stick to percentage. So there you go. All right, let's do some examples with this. So first off, this first one, we want to know that arc right there. So I'd say, okay, well, first off, let's find out the entire outer edge. So find the circumference. So arc length will be the entire circumference times how much of the circle we have. So I'd say, okay, well, the entire thing, the entire circumference, will be 2 pi times our radius, which we see here is 8. Now, how much of the circle we have? 106 is that central angle, which means that we're looking at 106 degrees. Oh, heavens. There we go. Over the entire 360 degrees, right? And that is the length of the arc. You're staring at it. You just got to simplify this, right? So to do this, I'm just going to check this whole thing in my calculator. Now, keep in mind, I'm going to leave the pi out for a hot second. We're going to do 2 times 8 times 106 over 360. And that's going to give me 212 over 45. Now, the reason why I left the pi out is if I put it in there, you'll notice that that fraction button disappeared. Pi is an irrational number. If you want an exact length, meaning no decimals, you can't include that pi. A few scientific calculators can do it, but most of them won't. So we know pi is supposed to be in the numerator. So if we do 212 over 45, right? Technically that was over 1. Pi's in the top. You just put pi in the top. So leave it out, do your calculations, put it back in where it should be. There's your arc length. Okay. Now this next one, similar idea. The difference is that you're looking for this entire edge here, but keep in mind the angle that you're given is actually for that arc right there. We could say, okay, so I know 30 degrees is that piece, which means what's the angle for all of the other stuff? Well, if you know 360 is the entire circle, then that means 360 minus 30, so 330 degrees is the remaining angle. So to find the arc length, that'll just be 2 pi times the radius, 7, times how much of the circle we have, 330 over 360. So same idea, I'm going to check it into my calculator. So we have 2 times 7 times 330 over 360. And then we have 77 over 6. And then I know pi, right? That's technically over 1, so pi is in the numerator. So it's still in the numerator now. Exact answer. If I wanted the approximate, right? If I wanted the decimal, you would literally just put the pi right in there, right? Put the formula in as it is, and 40.317 would be your arc length. Okay, so that is arc length. Let's talk about area of a sector. Okay, really similar idea to what we're doing before, except now we're looking at area. Now, a sector is just a part of the entire area. So that green highlighted portion is a sector of the circle, and if we want to know that area, well, we're going to do the exact same thing as before, right? All we need is the area of the entire circle, and then we're just going to say how much of the circle we're looking for. So hopefully you remember area of a circle is pi r squared. So in our case, our area will be 9 pi, because 3 is the radius, right? Plug in 3 there. 3 squared is 9, right? Which means that's how we got to our 9 pi. So that means the entire area of the circle, right? This whole thing is 9 pi. You can say, okay, well, I'm not looking for the whole thing. I'm only looking for 90 degrees of the whole 360. So your area of a sector formula is the same thing. Area of a sector equals the area of the circle times how much of that circle you're looking at. Theta over 360. And that's as crazy as it needs to get. So same process as before. So we'd say, okay, area of the sector equals pi times my radius squared times, we're looking at 86 over the 360. And that's it. Just plug it in and figure out what you get. So I'm going to go back and I'm going to say, okay, we have 86 of the 360. We're timesing that by 4 squared, or in other words, 16. And we get 172 over 45 equals 172 over 45. Now we had a pi in there to begin with, right? Technically that's over 1, which means it should be in the numerator, so 172 pi over 45 is our final answer. Now again, if you want the decimal, just plug it in as it is. So this next one, sometimes this number is going to be a little big for the calculator. You may need to use decimals depending on which calculator can handle. So because it gives us decimals, let's give this one as a decimal answer. But same process as before. So area of the sector equals pi times your radius, which is 2.4 in our case, squared, times how much of the circle we have over 360. Well, same idea as what we had for the arc length. That 52.9 is only that angle. My goal is to find all of this, right? I don't want any of the other pieces, right? If this is my goal, that 52.9 is literally the angle for everything except that. So to find what we do need, 360 minus 52.9, and then that should get us the actual angle that we're looking for. So in our case, that should be, I think it's 307.1, right? So that means that is our angle right there, 307.1, and now we're good to find it, right? That is going to be our arc length. Now, since we said we're going for the decimal, I'm going to keep the pi in there. So pi times 2.4. We don't need parentheses, so I'm going to put some, squared times our 307.1 over 360. There we go. And that means that approximately the area of the sector is 15.437. And then whatever the units are, this one didn't give us what the units were, so I'm just going to keep that as 15.437. But that is the approximate answer. If I wanted the exact, if you wanted the fraction version of that, keep pi out of it for a hot second, right? And then this one is 3,071 pi over 625 would be your exact answer. But that's like, the fractions start getting it small enough, like in pieces, that some calculators won't handle that. So just keep an eye on it, but there you go. Okay. Example 5, the last but not least moment. So given a circle defined by the central angle of 86 degrees. Stop. Break it down. Given a circle, shape, circle, right, is defined by a central angle of 86. Remember, a central angle is an angle at the center of the circle. That's what that means. This is your diagram, and you got all of that from the first couple of words. That's what all of that means. Okay, my 6 looks a little suspicious. There we go. All right, and that the area of the shaded sector is this thing, meaning that if you were to shade in the little sector of your central angle of 86, this answer, right, the area of that is 2107 pi over 20. Find the radius of the circle. So some radius there, we don't know what it is. Give an exact answer if possible. If needed, round it through decimal place. Okay. Whew. So first off, we know the area and we know the angle that gave us that area. We just need to figure out what the radius was. Well, I just happen to know the area of the sector is the area of the circle times how much of said circle we have. And plug in what we know. We just happen to know the area of the sector is 2,107 pi over 20. And we also just happen to know that the area of the sector comes from having 86 degrees of the entire 360. And hopefully you notice that the only thing that you don't know, the only variable in this, is the thing you're looking for, the radius. All right, so just plug in the information and then we can solve. Now, a couple ways to go about this. We could undo that division and then divide by everything that's multiplying, right? Because it's multiplication that joins the pi and the r, and multiplication that joins 86 and r. And all that technically is over 360. It really depends on what you want to do. I'm going to do it in little pieces. So I'm going to say times by 360. And I'm not going to bother with the degree symbol because those cancel. So times 360. All right, so on the right side, those cancel. And on the left, we now have 360 over 1. But I do know that that's going to simplify because that's 36 over 2, essentially, because it's multiplication, those can simplify diagonally. So I'm going to simplify that as I hit it. So 360 divided by 20. So in other words, that's 18, and that's 1. So making my life easier. So we have 18 times 2107, almost forgot that 7, pi, big number, don't know what it is, but there we go, equals 86 pi r squared. And same thing, that's being joined by multiplication. Undo multiplication with division, so I'm going to divide 86 pi, both sides. So those cancel, pi over pi, those also go the way of the dinosaur. And I'm just going to plug all of that into my calculator right there because, while I do like doing mental math, that's a little too large for my tastes. So we're going to take that number and divide by 86. Ooh, almost forgot it. And we get 441. So 441 equals r squared. Super nice right here. And you say, okay, how do I undo squares? Square root. Now, technically, there's a plus minus here, but we're talking about a radius of a circle. That is a length, and those can't be negative, right? Which means that you're really only looking for the positive square root of 441, right? Now, keep in mind, if we want to simplify that square root, that's actually 21 times 21. 441 is a perfect square, which means that 21 comes right out, and that is the value of our radius. Exact answer, we didn't need a single decimal. There you go. And that is the answer. And that's everything there is for arc length and area of a sector. So thank you so much for watching.